Okay, Matt Roscoe at the University of Montana, our course Math 326 Number Theory, and a video lecture on section 3.3, which is all about conjectures about prime numbers and their distributions. So let's get started. So I want to talk a little bit about primes and their distributions and some results that we have about them being close together. And then probably look the other direction and talk about their distribution from how far apart can they be. And then talk about a few interesting, I guess, results. One, the Goldbach conjecture, and then we'll talk a little bit about how the division algorithm has been used to type primes, and then talk about some functions that have played historical roles in the search for prime generating functions. So the first thing is, you should be, aware that the distribution of prime numbers within the positive integers is an area of intense and ongoing study in mathematics. There are lots of people working on these questions right now that have to do with how is the distribution of primes characterized across the integers, the positive integers. So you can find examples really quickly about primes and their distribution when they're very close together, and it sort of makes sense that 2 and 3 will be the only two primes which are consecutive integers. All other primes are odd, and by virtue of the fact that they must be odd, they can be separated by only one even integer at minimum when we disregard 2 in this case. So this idea that 11 and 13 are separated by an integer and they're both prime. 179 and 181 are both prime and separated by a single positive integer. And believe it or not, 6 followed by 10 zeros and 61, 1 followed by 10 zeros and 63 are also two prime numbers that are separated by a single positive integer. So we call these pairs of successive odd integers p and p plus 2 that are both primes twin primes, and it turns out that it's an open question whether there are infinitely many pairs of twin primes. So nobody's been able to prove that yet. Beginning in 2007, two large computing projects, Twin Prime Search and Prime Grid, have produced several record largest twin primes. As of September 2016, so relatively recent, the current largest prime pair known is this number, which turns out to be, these are two numbers that have 388,342 decimal digits. So you can see we're talking about extremely large numbers here, and the evidence is overwhelmingly positive that, given the scale of the largest known twin primes and the fact that we continue to discover larger and larger examples, it seems like the evidence is overwhelmingly in favor of the infinitude of twin primes. But as we know, evidence, in the absence of a hard proof, is only evidence and could be disproved. Who's to say we haven't found the last pair? So it's a proof of this, I guess, conjecture still has not been found. So not only can primes be found very close together, as in the twin prime conjecture, but they can also be found arbitrarily far apart. So given any positive integer n, there exists n consecutive integers, all of which are composite. So there is this theorem that says that I can find a string of consecutive integers which are all composite, which sort of gives us a sense that the primes should have insertable space in between them of any size, if this theorem is indeed true. So we should probably try to prove this theorem and then talk a little bit about prime gaps. So let's go ahead and move to the overhead here, and we'll try to prove this theorem. I think it's a pretty neat one, to be honest, because the proof is fairly straightforward. So given some n in the positive integers, we can, I should say, there exists some, I'll call it a string of n consecutive integers. And what's really interesting is that we can make those consecutive integers all composite. Okay, so that's our hypothesis. I'm going to switch pens because this seems to be getting a little light. So here's our proof. We proceed directly. Consider the set, and here comes. So what if we took n plus 1 factorial and we added 2 to it? This would be an integer. And then the next number, because it's got to be consecutive, we take that same n plus 1 factorial and we add 3 to it. And then the next one would be n plus 1 factorial plus 4, and we can continue that set. Now what we want is we want n of these, right? We started at 2, so we must have to go to 1 past n. So the last one would be n plus 1 factorial plus n plus 1. And what do we want our reader to note? This is n consecutive integers. Do you agree? And what so we have our consecutive set, and what we want to show is that they are all composite, right? So looking at the first, what do we note? So if we think about this, the first integer is this n plus 1, so there it is, n plus 1 factorial plus 2. Well, what does that mean? It means it's the number, n plus 1 times n times n minus 1 times ... all the way down to 2 times 1. And then what do we have added on to it? Plus a 2. And hopefully you can kind of see how this is going to work. The 2, that's here and here, those two things can be factored out. So it will be the same thing as 2 times n plus 1 times n minus 1 times all the way down. Well, the 2 has been replaced with a 1 times a 1 plus a 1. When I factor out the 2 out of this product, and I factor out the 2 out of this, I get this expression, which is 2 times some other number. And so what have we shown? We've shown that the first term is divisible by 2, right? I guess I'll keep that. See that all right? Yeah. So the first term is divisible by 2. We can see we can play the same game with the second term. We could pull a 3 out of that and a 3 out of this product. So I'll just say similarly, the second term is divisible by 3, and generally what are we going to call it? I guess the j'th term is divisible by j plus 1, right? Meaning all terms are composite, right? So we've constructed a list of n consecutive integers, all composite, as desired. So that means that given any n, I can give you n consecutive integers by simply, plugging into this, basically this form. So maybe we should play around a little bit with this just to make sure you're aware. What if I wanted 6 consecutive integers? So what if n was 6 and I wanted to construct 6 integers which are consecutive composite numbers? So what would that mean? So n here would be 6. So we'd start with n. What would be n plus 1 factorial plus 2? That would be the first term, right? So n plus 1 is 6 plus 1, so 7 factorial. Let's just put 7 factorial plus 2. That number turns out to be 842. So that means that n plus 1 factorial plus 3 is 7 factorial plus 3, so that'll be 843. And this will carry on until, I guess, 843, 844, 845, 846, 847, and 848. So these guys, by virtue of our proof, must all be consecutive integers, and they're all composite. I'll just all composite. And in fact, we know what divides it. 2 divides this one, 3 divides this one, 4 will divide this one, 5, 6, 7, and 8 will divide the last one. So here is an existence proof that we can construct gaps of arbitrary size that contain no primes, right? And so that means that primes can't come at regular intervals, or, well, at least that we can construct intervals of composites of any desired width. One thing to take into account is that this is not the first gap of, I guess, 6 consecutive integers, all prime, right? 1, 2, 3. Did I do 1 too many? I think I did 1 too many. N plus 2, yeah, I did 1 too many. 1, 2, 3, 4, 5, 6 of them. Sorry. So it's not the first set where we have consecutive integers. Let's see, which are all composite of that are 6 in width, and all we need to do is look for spots that occur prior to this one. So all it is really an existence that we can always construct one, but it's sort of a gross overestimate of where the first set of 6 composites in a row occur. I hope that's clear. It turns out that constructing strings of consecutive compositive integers proves that, we can, any size gap between primes exists. It doesn't really find where each gap occurs for the first time among the integers. I guess this is what I was trying to say before. So at present, we know the largest gap effectively calculated in the integers has length 1,442 with, so there would be 1,441 composites followed by a prime. So if we start with this prime and the preceding prime, then that's the largest gap that we've been able to encounter of consecutive, what would we call them, consecutive composites. And some gaps that are smaller than 1,442 are still missing, and the smallest gap is 796. We haven't found a gap between consecutive primes of 796. To give you a sense of what's going on here, let's take a look at this prime explorer. Let's see, where am I at? So if we have a gap of 2, what I have here are the number, I guess the natural numbers in the left-hand column, p sub n in the middle column. So that's the prime, the first prime, the second prime, the third prime, the fourth prime, and so on. And the gap tells me how far between that number and its preceding prime. So 19 is 2 past 17, 43 is 2 past 41, and 41 is 4. So the gap preceding the emergence of the prime is what's listed on the left, and we can see gaps of 2 are found. Of course, a gap of 3 won't exist because that would include that would imply that some prime number is even and the other is odd. So no gap of 3 exists. A gap of 4, though, does exist and is quickly found. A gap of 5 won't exist, again, the even-odd argument, but a gap of 6 will exist. A gap of 8 doesn't appear to exist, at least initially, but if we scroll down far enough, we do get a gap of 8 consecutive primes. A gap of 8 that separates consecutive primes 89 and 97. A gap of 10 doesn't appear to exist, at least in initially, but if we scroll down far enough, the first gap of 10 between consecutive primes occurs at 139, 149. A gap of 12 doesn't appear to be easily found, but can be found. A gap of 14 also seems to be found a little lower down. But I hope I give you a sense of what we're talking about in terms of gap searches in between primes. It's conjectured that there is a gap for every even multiple of the natural numbers. So 2, 4, 6, 8, 10, 12 on. And as we can see from this result, that has been verified up to 1,442. And it takes some extremely large searches to find these bigger gaps. So let's talk a little bit about the Goldbach conjecture. The Goldbach, he conjectured that in a letter to Leonhard Euler that every even integer is the sum of 2 numbers that are either primes or 1. So the conjecture is known as the Goldbach conjecture, and it stands to this day as an open question in mathematics. So let's go ahead and just make sure we understand what the Goldbach conjecture means. Every even integer can be written as the sum of primes or 1. So if we start with the even integer, and keep my cheat sheet out here. So if the even is 2, then the sum of primes or 1, well, that would be 1 plus 1, right? So you can see that the or 1 part really takes into account then the even number 2, because I think the rest of them, 4 can be written as the sum of primes, 2 plus 2. 6 can be written as the sum of primes, so what would that be? 3 plus a 3. 8 can be written as a sum of primes, so what would that be? Or 1. 7 plus a 1. Is that it? Yeah, I think that's it. So I guess you do need the 1 for 7. What about 10? Oh, wait, 8 you could also do as 3 plus 5, right? What am I doing? There we go. So I don't think you have to have the 1 except for in the 2 case. Let's see, 10 we could write as 3 plus 7, or we could write it as 5 plus 5. That's the sum of 2 primes. 12 we could write as, let's see, could be 5 plus 7, or we could use the 1 here, right? 1 plus 11. I should note that this could be 1 plus 5, right? And this could also be 1 plus 3. Let's see, 14 could be written as a 7 plus a 7. We could also write it as an 11 plus a 3. We could also write it as, what, a 13 plus a 1, right? So all of these are giving evidence of Goldbach's conjecture. Let's try one more. 16 we could write as, what, a 3 plus a 13. What about 5 and 11, right? So this is the sort of thing that Goldbach has conjectured, that anytime we have an even number, that we can always write it as the sum of primes or 1. Open question in mathematics to this day. One last thing to keep in mind is that sometimes researchers have taken a look at primes and tried to typecast them. So by the division algorithm, we could say that every positive integer can be written uniquely in one of the following forms. for some suitable n greater than or equal to 0, right? If we disallow 2 as the only even prime, then which of the forms do all the rest of the primes belong? And find examples of each in the integers from 1 to 100. So let's take a look at that question. And we'll make it bigger here. So what do we have here, right? So if we disallow 2 as the only even integer, so we're going to sort of cross 2 off of our list here and talk about the rest of the primes and talk about what form they'd have according to the division algorithm. So I think you should right away see that, well, 4n cannot be prime as 2 divides any integer of form 4n. You should also notice that 4n plus 2 cannot be prime, as 2 will divide 4n plus 2, which is the same thing as 2 times 2n plus 1, right? So what does that leave? So primes must be of form 4n plus 1 or 4n plus 3. One of those two types, right? And so let's take a look at what types they are, at least in the first 100. I guess the first prime's less than 100. So let's see. We're disallowing 2. What would 3 be? 3 would be in this category, right? What would 5 be? That would be a 4n plus 1. What would 7 be? That would be a 4n plus 3. 9 would be 4n plus 1. Let's see, so 11 would be a plus 3. 13 would be 2 more than 3, so it would be a 1. Let's see. Oh wait, but 9 isn't. 9 should be off this list. I'm sorry. There's a little error in my list. 9 isn't prime at all. Right? Okay. Sorry about that. Missed that. So it should be 5 and 13 here is all. Okay, so then what happens? Let's see. 17 would be, let's see, 16 is a multiple of 4, so it's plus 1, so 17. 19 would be down here. 23, let's see, 21. See, 20 is a multiple of 4, so 23 would be 4n plus 3. Let's see, 29 should be in the 4n plus 1 list. How about 31? 31 should be down here. And I will quit boring you with watching me talk and go ahead and fill in what I know for the rest of them because I have it here in my notes. So 37, 41, 53, 61, 73, and 89. Let's see, 31 would be followed by 43, 47, 59, 67 would be in there, 71, 79, and 83. Okay. And so one of the things that's been a curiosity for mathematicians has been the apparent appearance of this list, the 4n plus 3 types, being sort of greater in preponderance than those in this list, the 4n plus 1 types. And there's been quite a bit of mathematical discourse about whether or not one type or the other is more common, or whether or not there is an infinitude of both types. So I'll allow you to think about that for a second while I switch over to Excel, and we'll take a look at these types. So what you're seeing here is now n. So the second prime, now we've disallowed the first prime because we're getting rid of 2 and not considering 2, or considered 2 kind of a special case. But we can see that in green I have highlighted those primes that are of the 4n plus 3 type, and in red the primes that are of the 4n plus 1 type. And then over here what I've done is I've just sort of cumulatively summed when we get one. So at this point we have one of these types, and at this point we have one of both types. When we get to the fourth prime, then we've, disallowing two anyway, we have two of this type, one of this type. And one way we can kind of study whether or not 4n plus 3 types are greater than 4n plus 1 types is to look at the ratio of the cumulative sum of each type. So, at this point we can see that we have 7 4n plus 3 types, we have 6 4n plus 1 types, and 6 out of 7 is 6 out of 7 is about 85%. So 80, and I guess what we're measuring here is we're trying to determine whether, this thing bounces around above or below 1 to try to determine if indeed there are an equal or more of the 4n plus 1 compared to 4n plus 3 types. What's interesting then is to just graph this against n. So as the number of primes goes up, what does this ratio do in terms of the ratio of the various types? So if I go to insert chart, scatter plot it, and do something like that, I don't like that one. I'm going to get rid of the points. Insert a scatter plot without any points. There we go. And this is what you see, and it's the thing that mathematicians have noticed about this ratio, and specifically, I guess what they've noticed is that it bounces around primarily below 1, which would indicate then that there are more 4n plus 3 types than 4n plus 1 types. It every once in a while achieves the 1, and you can see the 1 here and here, and if I scroll down, I think we hit it very close to 1, but we don't ever quite get there again. We get close to 1 again. Here we're close to 1. And I don't recall, there is a 1 there at the 89th prime. We're equal, 44 and 44 of them, and so on. So it is a kind of an interesting question, whether or not there is more of one or the other type. I'll let you read your book a little bit about this, but at least I hope I've piqued your interest about this idea of typing prime numbers according to the division algorithm and division by 4. I guess what I would say is that there is a way of talking about this in general using the pi function. And the function here, pi with subscripts a comma b and input x, simply counts the number of primes of the form an plus b that are less than or equal to x. So to go back to our overhead, what does that mean? Well, in this case, what it means, we looked at all the primes that are less than or equal to 100 that are of the two forms 4n plus 1 and 4n plus 3. So we could talk about this by saying the primes of 4n plus 1, that's the a and the b in the division algorithm, I guess, less than or equal to 100. So how many of them are there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be 10 primes of the form 4n plus 1 less than or equal to 100, whereas pi 4 comma 3 evaluated at 100 would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these, and those are less than or equal to 4, 3, right? Did I miss one? The book is saying 13 here. Did I miscount? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Sorry, I miscounted. All right. So just a way of I guess communicating what we're doing up here in functional notation. And again, it's this question of when x is equal, is pi 4 comma 3 always greater than pi 4 comma 1? It seems like, at least our initial investigation seems like that seems to be the case, but I'll let you read your book for the punchline on that one. One thing your book does go into is a nice proof of the fact that there are indeed an infinite number of primes of the form 4n plus 3. You might be asking now, well, so is there an infinite number of primes of the form 4n plus 1? Again, I'll let you read your book to find the punchline for that. I don't want to give it away. A little carrot for reading your text. And one thing you should be aware of is that these are all you know, interesting, I guess, special cases of a huge theorem from Dirichlet that basically says if A and B are relatively prime positive integers, then the arithmetic progression contains infinitely many primes. So the progression is A, comma, A plus B, comma, A plus 2P, comma, A plus 3B, and so on. So in our previous example, A would be A would be 1 and B could be 4, so that would be primes of the form 4n plus 1, or A could be 3 and B could be 4, and that would be primes of the form 4n plus 3. So what that means is that, you know, 4 and 1 and 4 and 3, both being relatively prime pairs, we can construct infinite sets of prime, infinitely many primes of that form. So kind of interesting, not restricted to just 4 and 1 and 3, but we could think of, say, 5 and 1 and 3, or we could think of 6 and 1 and 6 and 5. So there's many routes for typing primes, and Dirichlet's theorem says that we'll always find infinitely many of them so long as A and B are relatively prime. A proof of this theorem, by the way, is not in your book and probably a little bit beyond the scope of this course. One last thing that we should look into, and I'll leave this also as a carrot, is this search for prime generating functions. So the idea of, can I find some function when I input a natural number into it, it always spits back a prime. And one intensely studied function of this form is this one that's staring at you right now. And let's take a look at how it behaves. So I'll step out of here and I'll open up this prime explorer polynomial file, which is also on the website. And so what I've done is I've created a prime explorer, excuse me, a polynomial explorer. N is here. Here's the function that we're given. I'm just squaring this, adding it to itself, and then adding 41, right? So 1 squared plus 1 is 2, 2 plus 41 is 43. And this tests for primality in this column, and then if it is prime, it gives it a 1 here, and then the total here is a cumulative sum. And the total divided by the number that have been, I guess, tested right now is 100%. And I'm not going to go too far down, but I guess my question is, what do you think? You know, I mean, it's pretty strong evidence. The first output is 43, it's prime. The second output is 47, it's prime. In fact, you know, I mean, the 11th output is 173, it's prime. The 16th output is 313, it's prime. You know, the 26th output is 743, it's prime. We still have 100% primality in terms of its prediction. There have been 26 primes tested, 26 resulted in prime. And the question is, will this ever end? You know, have we found some interesting polynomial, x squared plus x plus 41, that when inputted x, we always predict a prime? I'll just say that there is a forum to discuss this. If you participate in the forum, then I'll give you 1 point of extra credit on your next homework assignment. So look for that forum on our website. I think that concludes everything for today on 3.3. I wish you luck on your homework, and I'll see you on Monday when I return.